I'm Greg Alex Sr. from Med-Acoustics in Atlanta, and this is Introduction to Audiometry. It's a perfect class for someone who is going to do hearing testing for the first time. They might be doing hearing screenings, or they might actually do an audiogram, what we would call a pure tone, air-only audiogram. If that's you, then this is the class that you want. Audiology can be described as the study of the ear, hearing, balance, and related disorders. That's different than what we're going to call audiometry. Audiometry is simply something that tests your ability to hear sounds. And sounds vary based on two things: their loudness or intensity and the speed of sound wave vibrations. And we call that frequency. Hearing occurs when sound waves stimulate the nerves in the inner ear, in the organ of hearing, which we call the cochlea. And eventually the sound travels along pathways, the auditory nervous system, to the brain. Now, sound waves can travel to that inner ear through the ear canal, the eardrum, and the bones of the middle ear. We call that air conduction. That's normally how we hear. And if we test hearing using either a headphone or an insert phone, then it's air conduction testing. But sound waves can also travel to the inner ear through the bones around and behind the ear. And we can actually place a small vibrator behind the ear and test that way. This way we are bypassing the ear canal, the eardrum, the middle ear. We're bypassing all of that mechanism, and we are stimulating the inner ear, the cochlea, directly through bone conduction. That's another way of testing. So we have two ways of hearing: air conduction and bone conduction. The most common, of course, is air conduction. This is the minimum amount of anatomy that you should know if you're doing hearing testing. You can see here the external ear, and at the end of the external ear is the eardrum, and connected to the eardrum is what we call the ossicular chain. It's three tiny bones that move when the eardrum moves. So when sound wave vibrations hit the eardrum, they move these three tiny bones. Those tiny bones are the ossicular chain. It's called the incus, the malleus, the incus, and the stapes. Anyway, they're connected to the cochlea. That's the inner ear organ of hearing. It's this thing that looks like a snail, and you can see coming from that is the cochlear nerve or the auditory nerve. Okay, and this red section in between is what we call the middle ear. All right, so we have outer ear, middle ear, and the inner ear. You need all of that for the typical air conduction type of hearing. So we would describe sound in two ways. First of all, frequency. Frequency is measured in cycles per second or hertz, and hertz is abbreviated with a large H and a small z. That's how you normally hear it. So low frequency sounds, or bass sounds, they're in the range of 60 to 250 hertz. That's how many vibrations per second in the air, okay? And then high-pitched tones, this is, shrill sounds, high-frequency sounds, are 6,000 hertz or higher. Maybe somebody's screaming or something even higher frequency, higher pitch than that, okay? Frequency is pitch. Normal range of human hearing is from a low of 20 hertz to a high of 20,000 hertz, though most people cannot hear quite that good. What really matters is the range of human speech, and that's basically 500 to 4,000, even though there is a component of it lower than 500 and a component higher than 4,000. So we normally test from 250 through 8,000 for that reason. Now, some animals can hear sounds up to 50,000 hertz, much higher frequency than human hearing. Another way that we have to describe sound besides the frequency is the intensity. How loud is it? And intensity is measured in what we call decibels, and that's abbreviated dB with a small d and a capital B. Now, just to give you an idea of intensity, a whisper, someone whispering is going to be between 25 and 35 dB. They didn't want anybody else to hear it, okay? Conversational speech is about 65 to 70 dB. That's probably the intensity that you're hearing me now. Loud music, right? You go to some kind of concert, that's going to be between 100 and 120 dB. And then if you were standing right by a jet engine that was about to take off, that would be between 140 and 180 dB. Okay. Now anything higher than 85 dB can cause hearing loss if one is exposed to that over time. Okay. If it's very, very loud, like that jet engine, it might give you what's called acoustic trauma, and that's at least a temporary hearing loss, and even tinnitus, that's ringing in the ears, and that could be temporary or permanent, right? But generally, if you're in conditions, like if you're working in conditions that are 85 dB or over, you should be wearing hearing protection, because over time, even 85, 90 dB, like in a factory or something, certain places can cause a hearing loss over time, a noise-induced hearing loss. All right, so we had sound. We know how it enters the ear. We know about air conduction and bone conduction. We're going to be talking air conduction in our hearing test. And we know that sound involves both frequency, that's the pitch, and intensity, that's the actual degree of loudness. Now we test hearing with what's called an audiometer, and you'll be using a simple, what we would call a simple pure tone. That's the type of stimulus we're using. It's a pure tone, and it's a basic pure tone, air only, because it doesn't do air and bone, but air only audiometer. Okay, and that audiometer will have several components to it. The first component is an attenuator. All right, that's the intensity dial, where you're going to change the intensity from 0 maybe up to 90 dB or even 100 dB in 5 dB steps. That's called the attenuator. That's where we change the intensity. Okay, the technical name is attenuator. There's always an interrupter. An interrupter is the button that you press to present the stimulus to the patient. Now, the stimulus is going to be what I said before was a pure tone. All sounds are complex. My voice is complex. It's many frequencies that are varying in frequency and intensity as I speak, right? But in an audiometer, we use pure tones. Pure tones are simply one frequency. It's the only sound that is a single frequency, like 1,000 hertz, 2,000 hertz, 500 hertz, just one frequency and nothing else. It's not complex. It is a pure tone, right? Very frequency specific. We have a frequency control or frequency switch so that we can change from one frequency to another. Things like 250, 500, 750, 1,000, 1,500, 2,000, 3,000, 4,000, 6,000, 8,000. They're the typical frequencies. Then we have an air selector switch to go between left and right. We have either headphones or inserts that are plugged into the audiometer. I'll show you those in the next slides. We are going to determine either two things. We're either going to do a screening with which they either pass or fail, and I'm going to describe that to you, or we find the hearing thresholds. That's the lowest dB level that the person can hear the pure tones at a particular frequency. And we're going to plot that out and create what's called an audiogram, right? So those are the components that everybody needs to know. They're the controls that exist, the things we have to know about any basic air-only audiometer. Before we get started, we'll have to plug in the headphones, and this is what the back of a basic audiometer will look like. You'll have a place to plug in the left and right headphone on that headset. Two plugs, typically. And one will be blue and one will be red. Red is right, blue is left. So if they're marked left and right, you know that the blue one's in the left, red one's in the right. Sometimes they're color-coded, red and blue. They also have to plug in the power supply, either the power cord if it plugs in, or the power supply. And there might be one more thing to plug in, and it could be a hand switch. That's a switch that the patient can hold in their hand and push the button when they hear it, and a light or something comes on the face of the audiometer to tell you that they responded. Otherwise, they would lift their hand, raise their hand when they hear the tone. All right. And then you would put the headset on the patient, ensuring that the red earphone is on the right and the blue one is on the left. And we are talking about the patient's right and left. And you're adjusting the headband, headband's adjustable, so that the headphones are squarely on the patient's ears, and they're not going to fall down over time and sag below the patient's ears, right? You want to adjust the headband. And always have the patient facing away from you when you're testing, okay? You want them facing away from you because you don't want them to see what they're doing. And you want them to either push the response switch, if you have a response switch, when they hear the tone, or raise their hand when they hear the tone. And so you tell them they're going to hear some beeping sounds, and they're going to get fainter and fainter, lower and lower in intensity. But no matter how low they are, as long as they're sure they hear it, they are to raise their hand. They are to respond to that stimulus. Sometimes you can use these. These are called audio cups. They would replace the typical headband, and the headphones that come with the audiometer and are calibrated to it. Those headphones would be installed inside of these uh, audio cups. The audio cups are what we call circumaural enclosures. That's to do some noise reduction. You have to be testing in a very quiet room, very quiet place. And so someone doing testing would want to set their audiometer up in a place that is typically quiet. If there is no such place, nothing quiet enough, then if you don't have a sound room or a sound booth made specifically for hearing testing, and there is no place quite quiet enough, you have to get the quietest place possible. But then you can order audio cups installed, and they will do some noise reduction and help you get away with a little bit more ambient or environmental noise. Another way to test is with insert earphones instead of the typical typical headphones. These look like this, and you would pin them on to the patient like that. And then there is a tube that leads to a nipple, and on the nipple is a disposable ear plug that the patient has in their ear canal here. And you have red for right, blue for left, and that blocks out a lot of external noise too. So that's a very good way to do it. Though most people that use this type of audiometer will be using headphones. These are called insert phones. Here's the front panel of a typical audiometer. This may be the model that you have, or you might have a different make and model, but they all have to have things in common. The knob that you see here on the left is the intensity knob. It's how we control the intensity, the dB level of the stimulus. And this will go from 0 to 90 or 100 dB in 5 dB steps. And so you have an intensity control. The knob on the right is the frequency control, and that will change the frequency from 250 through 500, 750, 1000, 2000, etc., up to 8000. Then you can see right in the middle there is a button to push, a large button that you would use as your interrupter. That's the button you push to present the stimulus. You notice right above that there is a left and right button to change from the left ear to the right ear. Of course, we're going to do the same thing on both ears. And you can see on the display that right now we're at 1000 hertz. I don't know if you can see it, but we're on the right ear and we're at 25 dB. On the upper right-hand side in blue, you see some other buttons. These are to change the type of stimulus. The ones on the top, left to right. The first one, the one on the left, is for what we call a continuous tone. So it is whatever frequency and whatever intensity, and it is applied to the patient as stimulus whenever the interrupter, the stimulus present button, is pushed. Next to that, in the middle of those three, you see a dotted line that just represents a pulsed tone. So now it goes, instead of continuous tone, it is pulsed. Beep, 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 beep at the appropriate rate. That's another option of stimulus. It's usually easier to hear a pulsed tone than a continuous tone, especially when you get down close to threshold, the lowest level that a patient can respond to. That's their threshold. And so a pulse tone is a very good thing to use. I would advise that a pulse tone is always used, and give them at least 3 beeps. There's usually a light lighting or something on the display showing you that a beep is being applied. You'll see it blinking. The last one, the one over all the way to the right on those 3 buttons in blue, says FM. You probably can't see it. It says FM. That means frequency modulation. Sometimes it's called a warble tone. That's when you have a pure tone that is modulated. The frequency is modulated just 5%, 5 times a second. So it sounds like a warble tone, wah, 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 like that. It is even easier to pick out from the ambient noise that might be going on because you're not in a perfectly quiet place, and it's more interesting type of stimulus for children. It's used very often in pediatrics. You can even have a pulsed warble tone. Below that in the blue, the lower 2 buttons are to select either inserts or headphones. On this particular audiometer, you could actually have both, and you would choose which ones you're using because they are calibrated differently. Got to make sure you've got what the audiometer is calibrated for. And the audiometer should be electroacoustically calibrated once a year. So there's all the controls on the front panel of a typical audiometer. All right, so there's 2 ways to do it. You can either do a hearing screening or determine the hearing thresholds. The easiest thing is a screening. This is for patients who you're going to say, well, they either pass or they fail. If they pass, then there's no other testing that's usually done. If they fail this test, then they are referred for additional testing. When you do this, you would set the intensity at a particular level. And it's either going to be 20 or 25, whatever is your clinical standard, and usually the physician or whoever's in charge, supervisor, will make that decision. If you had a very quiet place or a sound booth to do it in, this is a booth, a room, it's usually a metal room, could be all kinds of different sizes, but it's meant for hearing, designed and installed there for hearing testing specifically. All right, well then you certainly can do it at 20. If not, then 25 is what I would recommend. Otherwise, you might have too many false positives. That's when a patient fails when he really shouldn't have failed, right? But it was just due to outside noise. If you are worried about this, we could always come in and test your environment with a sound level meter to determine whether it's quiet enough for screening at 20 dB. But 25 is normal in like all the school systems in Georgia, for example, and Alabama use 25, probably Florida too. The frequencies that are typically used in a screening are 500, 1,000, 2,000, and 4,000. That is the speech range, the most important of all of the frequencies, because most of speech is comprised of those frequencies. And a patient passes if he's able to respond. In other words, you could put it on 25 dB at 500, present the tone, beep, beep, beep. He raises his hand that he heard that. Same thing at 1,000, 2,000, and 4,000. If that's the case, they pass. But the patient is referred for additional testing if they fail to respond at one or more of these frequencies. The best thing to do is if you are going to do a screening, set it up, put the headset on yourself, and make sure that in both ears you can hear all four frequencies at whichever level you're screening at, like 25 dB. Because if you have normal hearing and you can't hear them in that environment, then of course the patients aren't either, and everybody's going to fail. A whole bunch of false positives. You don't want that. You had to have a place where people can pass when they're supposed to pass. I hope that makes sense, and that's a typical hearing screening. Now we'll talk about a more detailed test, and that would be to actually come up with an audiogram. Now we're going to test all the frequencies from a low of 250 typically through 8,000. Okay, and we would begin at 1,000 rather than 250. Why? Because it's easier for the human ear to hear frequencies in the middle of the frequency range rather than the low end or the high end. So we go to 1,000 hertz and we start there, just getting the patient used to listening to the tone and responding by either raising their hand or pushing the response switch. And then once we determine their threshold at 1,000, then we'll go to 250 and proceed to 500, 750, back to 1,000. It should be the same thing we got to begin with, and then onward to 8,000. And the intensity is manipulated like this. If we were testing our first frequency, 1,000, we would start at 40 dB. Notice I have 40 dB HL here. HL means hearing level. The audiometer is calibrated in dB HL, decibels of hearing level. That means that at 0, it doesn't mean there's no sound. It doesn't mean there's zero sound. That would be 0 SPL, sound pressure level. But dBHL, hearing level, just means that at 0, there is zero hearing loss, no hearing loss. And if a person had a threshold, if the lowest level in dB that they can actually respond to saying that they hear the tone, if that lowest level were 50 dB, their threshold would be 50 dB HL. They have 50 dB of hearing loss. Perfect hearing, they would actually have a threshold of 0 at every frequency. dBHL means decibels of hearing loss. 0 means no hearing loss. All right, so we would begin at a super threshold level. 40 dB is typical, okay? But if they don't hear it at 40 dB, then we would apply the stimulus with the interrupter button at a higher level. I go up in 20 dBs. Like if they don't hear it at 40, I go 60. If they don't hear it there, go to 80. Hopefully they hear it there, and then I proceed down, right? But I want to start at a super threshold level, right? The super threshold simply means above the lowest level they could hear. For most people, it'll be 40 is a good place to start, at least. Anyway, you would advance the intensity downward by 10 dB. If they heard it at 40, you would go down to 30. If they heard it at 30, you'd go down to 20. If they heard it at 20, you'd go down to 10, right? You go down in 10 dB increments. Now, if there is, once you have no response, you go up by 5. So you're down by 10 when there is a response, and then when there's no response, let's say the last response you got was at 20. You went to 10, there was no response. Now you would go up to 15, right? And if there was a response at 15, then that would be the assumed threshold. But once you find the first assumed threshold, the place, the lowest intensity at that frequency, then you drop down 10 below it and come up by 5 again. You would drop down to 0. They don't hear it. Go to 5. They don't hear it. Go to 10. They did hear it. Bingo. 10 is the threshold. Okay? That's why you advance the intensity down 10 dB if there is a response, and up 5 dB when there's no response until there is. And that's how you arrive at the threshold. You actually will get it twice to be sure that that's it. You'll get it on the way down and the way back up again. So again, if we started at 40 and the patient either pushed the button or raised their hand, they heard it, went to 30, they heard it, went to 20, they heard it, went to 10, they didn't hear it. Now, I would be going up. I'd go up to 15. And if they didn't hear it, I'd go up to 20. They heard it again, that's the second time at 20, then I would take that. But if they heard it at 20, I went down to 10, and there was no response at 10, I went up to 15, and then there was a response, then I'd want to drop down 10 below that, right? And come back up. So I drop down to 5, then I'd come back up to 10, and then 15, and if I got it at 15 again, I would take that, okay? So that's how you do it. It's down 10, up 5. That's what you got to know. You also have to know that red is right and left is blue. And you would plot those thresholds, okay? And you would come up with an audiogram like this. Notice that on this vertical axis here, there's a 0 line. 0 is right here, and then 10, 20, 30, 40, and up. If our audiogram were plotted right across this 0 line, that would be absolutely perfect hearing, right? You might not be able to get that in your environment, and that will be okay, unless your environment is way too noisy to test. Then everybody would fail. But anyway, see, they determine the threshold, and you would mark the threshold on the graph. Notice the intensity is on this vertical axis, and on the horizontal axis are the frequencies, right? 250, 500, 1000. Then 1500 is a half octave. That's why it's a dashed line. 1500, 2000, 3000, 4000, 6000, and 8000. It's divided in octaves, right? The octave is a doubling from 250 up to 8000. And there are a few in this range, the higher frequency range, there are actually half octaves, and they would be 1500, 3000, 6000. They're half octaves. There's a half octave between 500 and 1000 too, 750 if you wanted to do that. But anyway, if we did all these frequencies, here 20 dB was the threshold, so they put an X. X is for left and O is for right. Everybody knows red is right and round. You can remember that. Red is right and round. All right. So in the left ear, they got maybe, I don't know whether this is 20 or, you see if it's actually 20, you'd put it right on that intersection of the 20 line and a 250 hertz line. If it's 25, you'd put it in between. All right, so this I can't really tell whether it's 20 or 25. Let's say it's 20 and should have been right on that intersection. The X's are the left ear. Then at 500, they heard it at 10 dB, or maybe it was 15. Maybe that's supposed to be in the middle. Uh, this one, 1000, they heard it at 15. 15 was the lowest level, right? So when they went down, they got it at, when they were doing it at 40, they got it, and 30, they got it. And this is on the left ear. They got it at 20. They went to 10. They didn't get it. Then they went up by 5. So it's down 10, up 5, 15, and they got it. Then they dropped down below that by 10, come up by 5s, got it at 15 again. 15 is the threshold, right? That's the method, that down 10, up 5 method. If you have your first assumed threshold, you're going to drop down 10 below it, come back by 5s. Get it twice, then you got it, and you plot it. An X for left and an O for right. Now here, the left and right, here, this is at 1500 hertz. The left and right both had a threshold, both ears, at 20 dB. So you have an X within a circle, an X within an O, right? Here they were both at 40 dB. Here, 60 dB on the left. This is at 3000 hertz, but 65 dB on the right. It was the same thing at 4000. 60 dB threshold on the left and 65 on the right. At 6000, 65 dB on the left and 70 dB on the right. And then at 8000, the threshold was 70 dB on the right, and on the left, it was 75 dB. So we would say that this patient has a high frequency hearing loss, because in the higher frequencies, these are down. Now, how much hearing loss is there? Okay, here's the last slide. Oops, sorry, I forgot I was going to show you some different audiometers. Here's different makes and models of audiometers. This is Mako, is a very popular manufacturer, a Mako MA27. You can see the intensity and frequency controls. You can see the interrupter that you press to apply the stimulus. And then these buttons, their function is displayed on this digital display here. And it would be one for left and one for right, one for maybe choosing a steady tone and another for a pulse tone, things like that. Here's another audiometer, same manufacturer, Mako MA25. Again, you have a control for intensity and frequency, an interrupter or tone presentation switch, and then these buttons are actually indicated on this digital display as to what they do. You use them to change ears and apply what type of stimulus you want. So what about analyzing the audiogram? Okay, well, you see this, 0 to 20 dB is considered normal hearing. We normally don't do anything about correction for hearing when it is between 0 and 20 dB. All right. Now, if we find a valid hearing loss on a child in school, then we might put them, even though it's a mild hearing loss, we want to take special consideration of that, have them in the front of the class and have the teacher know about it. But for adults, 0 to 20 is not a problem. And then look at this, from 20 to 40 is considered a mild hearing loss, okay? From 40 through 70 is a moderate hearing loss. 70 to 90 is a severe hearing loss. And then above 90 is a profound hearing loss. Some audiometers actually go up to 120 dB HL, and that's a profound hearing loss. So anyway, this type of audiogram would tell you that this patient actually has a severe high frequency sensorineural hearing loss, because his three highest frequencies, right, 4000, 6000, and 8000 are in this severe area. Some of the frequencies before that, uh, uh, 2000, 1500, maybe in this moderate area, and then 1000 might be in this mild area, and it's just the low frequencies that are normal. So when this patient is hearing, he actually will say to you that people mumble all the time. And it's because he hears the low frequencies okay. Low frequencies are the vowel sounds, and the consonant sounds are high frequencies. So when he hears speech, he actually hears the vowel sounds only, and he misses the consonant sounds. So it sounds like everybody's mumbling. Don't mumble, speak clearly. Right? You are, it's just that he's missing the consonant sounds and trying to make them up. Right? And it's a very difficult time communicating because of it. And the proper hearing aid would be adjusted so it doesn't provide amplification, or what we call gain, in the low frequencies, but the appropriate amount of gain at these different high frequencies to bring them all up to within this normal area that he would hear normally. All right, so I hope that that's helpful. If you need any more information, you can always contact Med-Acoustics, and we'll help you in any way we can.